Hi, welcome to the talk. The data will not come to the astronomer. I'm Adam Thornton. I work for the Large Synoptic Survey Telescope. If you want to snap a shot of the screen, the QR code takes you to this presentation slide. So this talk is licensed under Creative Commons Attribution 4.0 International, so feel free to plunder it. Just tell the world that you plundered it from me. So I'm going to do three basic parts to the talk. The first is an overview of the LSST itself. The second one will be sort of traditional methodologies in astronomical data analysis. And the third part will be about the interactive notebook environment I'm developing for the LSST project and why I think that's a better solution than what the current status quo is. I'll also talk about some challenges we discovered while implementing it at the LSST. So hopefully you can learn where some of the sharp corners are and not have to bump into them yourself. So LSST is a large survey telescope project. It's funded mostly by the National Science Foundation, but also the Department of Energy, and then a host of other institutional and private donors. So the goal of the LSST is that we're going to take a 10-year survey of the southern sky. We're building a telescope on a mountaintop in Chile. And effectively, every 3 nights, we will pan a camera across the sky for 10 years. This will enable detection of a number of things at all astronomical scales, from near-Earth, possibly Earth-impacting asteroids, out to cosmological questions. If you were in the keynotes today and saw the LIGO speech, one of the things that LSST will be extremely useful for is when LIGO detects a gravitational wave event, that's not particularly well localized. They can tell us, it's over there somewhere. LSST will, assuming that over there is somewhere in the southern hemisphere, will have a picture of that patch of the sky within 3 days of the event. And then a whole bunch of stuff at intermediate scales as well. So to do this, we are collecting an awful lot of data. Roughly 20 terabytes of data a night will be coming in from the telescope. To put that into some perspective, I'm sure you've seen many Hubble Space Telescope perspectives. We collect the entire HST lifetime data set scale each week. Our final image collection after 10 years will be approximately half an exabyte. That includes over 1 trillion photometric measurements of celestial sources. Now, most people are not going to use the image catalog directly. Instead, they'll use the catalog, the database that we produce. And that's going to be on the order of 15 petabytes, and it's going to be tens of billions of rows in a database, and those rows will each have a complex structure. So obviously that's too much data to move around easily. It's probably not going to fit on your laptop even in 2032 when we're done with the survey. And so rather than move data to the analysis environment, we need to situate the analysis environment next to the data. This isn't the way astronomical analysis has traditionally been done, although for recent survey projects, it more or less is. But first, what is the data we're collecting? Here are some fun facts about cool stuff we're going to see. 10 to 40 million active galactic nuclei, which are quasars, which are what happens when the supermassive black hole in the center of almost any galaxy is actually actively ingesting something, and little bits of it are escaping as it's being gobbled up. We'll see about 300,000 supernovae each year. Now, the current worldwide detection rate is about 7,000, so we're getting a 40-fold increase from a single instrument. A fun Fermi problem, a galaxy the size of the Milky Way, which is a few hundred billion stars, sees one supernova every few hundred years. We will see there is one supernova in the observable universe every 10 seconds. Feel free to do the order of magnitude calculation. We're going to observe roughly 20 billion galaxies and roughly 20 billion stars, most of those within our own galaxy, which means that if we were handing them out, every person on the planet could have 3 of each. So there are some very good resources about the LSST. Andy Connolly's TED Talk is great if you've got 20 minutes to spare to listen to it. It's a few years old now, but it's well worth seeing. And then there's the page of key numbers, which is a handy reference for 20 terabytes a night, half an exabyte, etc. And then if you're really into it, the overview paper is about 60 pages, is about 400 co-authors. It's heavy going. It's probably more than you want if you are not an astronomer, but it is all of the science goals laid out in one place. So how do we see this with the LSST? Well, the first question is, how faint an object can we see? The depth. Astronomers use a scale called magnitude. The faintest thing you can see with your naked eye is about 6th magnitude on a good dark night, someplace far away from light pollution, clear skies. By the way, if you're a software developer and you're complaining about technical debt because you're having to use a language written in the 1970s, astronomical magnitude, that is, 1st magnitude being really bright, 6th magnitude being the limit of what you can see, dates back to about 150 BCE and Hipparchus. We still have the star catalog from Ptolemy in 150 CE, and that's basically the same numbers. And the numbers have been kept all the way through the systemization in the 1850s to the present day. Now, a single visit from the LSST can see 24.7 magnitude, which is very, very dim indeed. And if we stack all our images over 10 years, we can get object detection down to 27.5. So that's 30 to 400 million times fainter than the naked eye, depending on whether you're talking about single visit or stacked depth, which doesn't mean much. I mean, I'll give you something else that doesn't mean much, but is a little easier to visualize. Take a golf ball, illuminate it by the sun, now put it in the moon's orbit. We can see something that faint on a single visit. It's not the deepest telescope, but it turns out the depth isn't quite everything. We also can see an enormously wide field of view, and that's why we can do this survey. This is a picture by Nate Lust based on 8 Hubble Supreme Cam collaboration data, showing the moon superimposed over the field of view. So roughly 40 full moons, take a CD, hold it at arm's length, and that's about the size of a single image taken from the LSST. Because we do that and we have a 30-second visit and we just move it around the sky, that lets us cover the entire southern sky in 3 nights. So the camera itself is 3.2 gigapixels. It's the largest digital camera ever built to this point. That's its former project manager, Nadine Kurita, standing next to it for scale. The camera itself is built of 189 4K by 4K sensors. So if you're displaying that on 4K TVs, you could basically tile about half a basketball court with that for a single full resolution image from the LSST camera. We do 2 15-second exposures. That both lets us do atmospheric and cosmic ray rejection. It also turns out that you can do a little bit of science, that if you have a close, fast-moving asteroid, you can actually see its motion between the 2 exposures. The other thing I found out last week at our all-hands meeting is that based on the volume of the camera, you could fit 240 corgi puppies into it. So the mirror is exceptionally complex. Basically, it's a 3-mirror system, but mirrors 1 and 3 are built on the same piece of glass. Light comes down out of the sky into the telescope, hits the outer annulus, is reflected back up to a convex mirror suspended by the camera, back down into the tertiary mirror, which has a different curvature than the primary, and then up into the camera. It's an 8.4 meter mirror, so that's 27-ish feet. It's got the effective light collection area, because it's this multiple design, of a 5.6 meter mirror, which is not the largest, although it's pretty large. However, because of the complex shape and curvature and the structure needed to support it, it is the largest monolithic piece of glass ever fabricated. All this doesn't come cheap. The observatory itself is about a $500 million project. The camera is $165 million of that. And the mirror, the primary tertiary mirror, is about another 25. Operationally, it's expensive, but for something of this scale, I found it surprisingly not expensive. It's $1 a second, $100,000 a day, or $35 million a year, which, you know, is a lot, but not a lot on the grand scheme of things. So this is a little site overview taken by Jacques Sabag, one of the telescope and site people, in December. He did a drone cam flyover, and you can see, I think I have a pointer here. Maybe. Well, I'm sure I do. I just don't know how to use the thing. Anyhow, you can look. You can see some people walking, some vehicles. That's the scale of it. It's a pretty big building. That little thing on the next hill is the calibration telescope we use to determine atmospheric characteristics to correct for the images we're taking. And this is up on the web. If you search on YouTube for LSST drone flyover, you will find it. So the other thing I wanted to point out, the background image here, which you can sort of see, is the construction site in April. This was just taken, this is a webcam image from Summit Camera 2 that I happened to catch when I thought, oh, I wonder what the summit looks like right now. Moon at the top, Venus there, and then you can see the profile and where the dome is going to be. All right, so on to how astronomers typically collect and use data. The historic model has been you've got a machine on your desk that your department paid for that's generally pretty beefy. You've got some astronomical software. Usually you, the astronomer, wrote it yourself. And it's designed to investigate a particular hypothesis about high redshift quasars or whatever it is you study. It is almost never general purpose because, after all, in astronomy, you're not rewarded based on the quality of your software engineering. You're rewarded based on your astronomical results. And typically, you've got data you got from observation runs on a telescope, and that's stored locally. There have been some attempts to do more generic astronomical software, and in general, those have been written by many astronomers, which is arguably much worse than being written by a single astronomer. So there are obvious failure modes that, in the interest of time, I'm not going to go into, but it comes down to, hey, it's a departmental machine, not a professionally run data center. So LSST data is not going to be immediately public. It will be made world public, I believe, 2 years after initial publication to rights holders, which means there may be a lag of up to 4 years from actual observation to world public data. But there are already extremely broad data rights in the sense that all US and all Chilean astronomers, or actually anyone associated with a US or Chilean academic institution, has rights. Turns out that that's already about half of the worldwide astronomical community. So roughly 10,000 out of 20,000 people. And of course, you can collaborate. There are rules on how you can collaborate so other people can gain access rights. So effectively, if you're an astronomer wanting to work with LSST data wherever you are, it's probably going to be fairly straightforward to do. The other interesting thing is that, to a first approximation, none of our image data will ever be seen by a human. Right? We're collecting 20 terabytes a night. That's a lot of imagery. Most of these most of these images are never going to be seen by a person. They are going to be analyzed by software. The alert stream broker will say, hey, there's something interesting over here, and depending on how interesting, someone may eventually go look at the image. So that means that we're moving into a different phase of analysis than has been traditional in astronomy. In fact, our new model looks a lot more like particle physics, where you have enormous amounts of data, you have very large collaborations, and it isn't so much the raw data and your ownership of it that is the professionally interesting part, it's how you analyze that data. So what we need to do, and what I have been working on for the past year, is facilitating rapid iteration of analysis, which is something you also heard a bit about in the keynotes, that we have this enormous ocean of data. We want a way for researchers to think about things they find interesting and iterate swiftly through a bunch of hypotheses so they can throw out the ones that do not look particularly interesting. And then once they have something they like, then they can run it over a large subset of the data on some sort of batch system. So that is effectively what we're looking at. The interesting thing about doing it is that we have we have some idea, but we cannot specify the subset of data we want people to work on in advance. Any given astronomer working on any given problem is probably only going to need a few terabytes of data to determine whether or not the hypothesis looks fruitful. But that's a few terabytes out of 15 petabytes, and so we have to have a way to have arbitrary selection of data from that. So that in turn means you don't need a great deal of computational power, you don't need a great deal of data I/O speed to do the interactive, iterative portion of your analysis. But having access to the entire data set so you can peel out whatever subset you want is completely crucial. That in turn means you've got to park your That in turn means you've got to park your code next to the data. So let's imagine a better way to do astronomy. And given that you're at this conference, you probably know where this is going, but bear with me. So it'd be nice if, even if you've got a very complex analysis stack, which we do, you don't have to invest a lot of time in learning how to set it up, which turns out to be huge. And it'd be really nice if what you really needed was a web browser, so your laptop is perfectly fine. You're not doing any of the heavy lifting on it. Some reasonably nice way that you can log in wherever you are and not have to manage a whole bunch of different identities to do analyses at different sites would be great. Just choosing an arbitrary subset of data because the whole thing is available to you would be awesome. And then maybe if the infrastructure is running on professionally maintained machines, then you don't have to rely on some poor uncompensated graduate student who's acting as the departmental sysadmin and is an astronomer and not an IT professional. So we think we've built this. The interesting thing is that the hardest design goal is to make something that doesn't make anybody's life significantly worse while making most or everybody's life better in a lot of ways. Obviously, the current system we have is not the greatest because in part because the analysis stack is so huge. I myself have never been able to install it from source, from scratch. Never succeeded. I've installed it from binaries, but actually building the entire thing from source, not once. It has typically it takes experts several hours to set up on any new release they want to deploy. It typically takes newbies weeks to months, and that also consumes a lot of time from the people who know how to do it, as the newbies have to ask for, hey, how does this work? The stack itself is kind of riddled with technical debt. A lot of the design, some of the implementation goes back to SDSS, which became operational in the year 2000. Our software stack has been under development for more than a decade. I believe that SDSS was also being worked on for more than a decade before the project went operational. So we've got, 25-ish, 30-ish years of code buried in there. The thing is, it also gets the job done, and these are complex and difficult problems that people who know a lot about it have spent a lot of time working on. So at some level, the complexity is irreducible, right? You've got thousands of years of astronomer knowledge embedded in this software. So who do we have to please? The people who are using the pipeline, that's the easy group. And in fact, we've been getting great feedback from our commissioning group who just want to use it to analyze data, do calibrations, do regression analysis, make sure that if they reanalyze SDSS data, that the results they get from our stack match more or less the results that SDSS got. These guys love it because all of a sudden, rather than having to spend that weeks the first time and hours even once they know what they're doing, they just point a web browser to an endpoint, type import LSST, and they're up and running. But we also have to keep the pipeline developers happy. Now, these are the people working on the stack. In general, nobody works on the whole thing because it's very big and very hairy. Everyone's got a particular little area of expertise they work on. And we have to support the model where they get a snapshot. It could either be a release version, which we do about 2 of a year, or it can be a weekly release. They work on their stuff. They get a PR they like. They PR it back to the trunk of the project, and then it gets merged. So we need to support that. And then there's the established astronomical community. These are the guys, guys and girls, but frankly, mostly guys, who bring in the big grants because they are the guys who have been doing astronomy since the 1970s, have tenure, have the established research facilities. They already know how to do astronomy. They've been doing it for a long time. They've been doing it for so long that Fortran and FITS are probably their tools of choice. This is not ideal in a modern world, and it's not necessarily ideal from a sort of notebook-centric, high-speed iteration world, but we have to keep them happy. They bring in the grant money, and they really do know their stuff. So what we've done is cheated, right? We've created an environment in JupyterLab that mimics a multi-user Unix system on which you have an unprivileged user shell, and those guys can more or less ignore the notebook aspects and just pop open a terminal and do the same things they've always done. Turns out there's an interesting uncanny valley problem here in that what you give them sure looks like an unprivileged user account on a big shared departmental Unix machine. But it isn't, and then they get upset when they can't run X clients on it, they can't SSH into it to do stuff, and the one that I have a little more sympathy with is, well, I'd like to run Emacs, but every time I hit Command W, my browser window closes, which, yeah, okay, fair enough. So then you have to worry about operations. Now this diagram of the Docker security model has been contributed by my colleague Abby Yaka. It's not entirely unfair. The nice thing is if you do go to the efforts to provide your previous group of users with what looks like a familiar environment, you also end up with a well-characterized container such that you can point out, okay, we know the versions of everything running in it. We are not running any network services other than JupyterLab itself, which is only accessible through this one HTTPS endpoint that uses two-factor authentication. And when you can show that you completely characterize the contents of the container and that the network ingresses are limited, then it's generally not any worse than whatever the previous setup was. I mean, you still have the issues that you have an unprivileged user with network access to much of the rest of the cluster, but you did already if you had a centralized machine that was talking to the database that held your catalog. So this is the part that is supposed to make everyone sit up and gasp, but of course here, how we've done this is with Kubernetes plus JupyterHub plus JupyterLab, right? Kubernetes obviously won as the container orchestration framework. All of the big three cloud providers give you a managed Kubernetes installation. In all cases, pretty easy to use. I have a lot more experience with Google Kubernetes Engine than AWS or Azure, but I understand those work pretty well. We chose to go with JupyterLab because we don't become operational till 2022. And I figure that by then, JupyterLab is very likely to be the de facto way you run notebooks. If not, it may be the thing after JupyterLab. And I expect we will end up replacing the lab portion of it several times over the 10-year operation of the project. You know, there will be future iterations. Just as JupyterLab is sort of replacing classic notebooks, something else will come along eventually to displace JupyterLab. And I figured, why should we bake in more technical debt early on? You know, I've still got 3 years for JupyterLab to solidify, and I'm pretty sure it will be. And then JupyterHub is the obvious way to do brokering for authentication and user container dispatching. It's been nicely architected. The Authenticator and the spawner let you do a whole bunch of really sophisticated stuff in terms of how you spawn containers for different users. So abstraction layering, essentially Kubernetes just takes you farther up the stack than we've been before. Not only do you not need to worry about hardware details, which would be virtualization, or distribution details, as containerization gives you, you also get to stop worrying about container lifecycle and intra-application networking. So I think that this is going to fundamentally transform the way astronomers do their analysis. Because it's really the first time we've had access to an abstraction layer that lets you do this, that you can specify an architectural pattern and get someone like me who has done infrastructure for most of his career to design that piece, and then let the smart people go work on all the analysis bits that are delivered as the payload for it. And that is nice because then you don't really need to worry about managing the infrastructure if you're running on something with a well-managed Kubernetes deployment and you followed reasonably good practices in putting it together. So to do that, you obviously need to separate your plumbing from your application. In our case, the application is just the JupyterLab container that contains the analysis stack. Then away you go, right? You put in a lot of effort up front to get the design right, and then it more or less runs and you replace the user containers as you need to. It turns out that packaging the user component is a really easy problem. You need a container that will start a JupyterLab server, and you need some way to present whatever your analysis environment is as a Jupyter kernel. In our case, that is these 9 lines of Python, which probably took me all of 15 minutes to write. Right? I mean, you can look at, we get the LSST environment set up. We turn on a couple of the major packages. We look for individual user setups to run so that users can have individually customized environment. And then away we go with the Python kernel. Done. So scaling in this Kubernetes-ified world becomes really easy. If you're running at a public cloud provider, you probably can just turn on auto-scaling. There are some subtleties to it, but to a first approximation, that's what you do. Step 2 is do some sort of closed feedback loop to modify the pod width in your deployments. Well, now that I'm scaling out to 40 clusters, I need to have 3 Jupyter Hub servers instead of 2, something like that. And that's it. There's no step 3. Like scaling, done. The nice thing about public providers, of course, is that as long as you have credit remaining on your credit card, they will happily give you as much capacity as you ask for. That can also be dangerous. So the other great thing is that I've worked with a lot of open source communities before. Jupyter is right up there with the best of them. It's a very welcoming community. People are extremely friendly. JupyterLab itself is changing really fast. So here's my dirty little secret for getting stuff you want done. Write it. Right? Write something. It'll probably be horrible, but just write something that gets the effect you want. Then go on the Gitter and say, hey, I did this neat thing, and here's how I did it. And then you step back and wait for the gasps of horror. And then the people who really know how to do it will be like, have you considered maybe doing it this way, which isn't quite so gross? The terrifying thing about this is that after a few months, you find yourself saying to someone who comes along and says, I did this really neat thing. Maybe you should think about, and then it's too late. You're totally co-opted. You've bought in, and it's great. So thank you. So I'm now going to talk briefly about the implementation we're doing of Lab Hub and Kubernetes at LSST. I realize you can't read that diagram at all, but effectively that's the architecture, right? The green box inside the blue box is Hub. The blue boxes inside the outer green ring are the lab containers. And the red stuff is external data sources and data consumers we're connecting to. So it looks about like you'd expect. Once you're building the deployment, by all means, do it in some automated fashion. I did what I always do, which is build my own build system, which is a terrible idea, and don't ever do that. Rather than doing it that way, and our implementation is on GitHub. In fact, all of the stuff we're doing at LSST is available under open source licenses. The science stack is mostly GPL. Our stuff, the infrastructure stuff, is mostly MIT, so you can borrow it much less restrictively. Anyhow, take a look at what I did. It's interesting. It may give you good ideas. Don't do it that way. Use 0 to Jupyter Hub instead, which is a terrific project from Project Jupyter. It's how they're doing Data 8 at Berkeley, I think. They use Helm. I do not use Helm as a layer on top of Kubernetes to manage the application. The part that Helm does is the templating, which is easy. The part that Helm doesn't do is sequencing, which if you have persistent storage, say, you need to bring up your NFS servers before you can create any of the stuff that relies on it. Yeah, you can do multiple Helm stages, but at that point, you're not getting much over just doing the templating yourself. Terraform looks like it's got a pretty good model for doing this. I imagine by this time next year, there will be some clear way to do sequenced multiple container deployments. Whatever it is, and it may be something Helm grows, it may be Terraform, it may be something else. Use that rather than rolling your own if you can. So we ran into a few specific challenges as we were writing our implementation. The first and obvious one is authentication, right? It turns out that authentication is full of nasty corner cases and really just make someone else do it, which is what we did. OAuth turns out to be an excellent, well-supported way to do interactive web authentication, which is obviously what a notebook environment is. So I've got 2 reference implementations in the LSST deployment. which correspond, of course, to the prototyping I do at GKE and then our actual deployment, which is at the NCSA, National Center for Supercomputing Applications in Illinois. One of them uses GitHub Auth, one of them uses CI Logon plus the NCSA ID provider. But because they're both OAuth, they're very similar, and they rely on almost entirely the same underlying code. However, just saying, well, do you have an NCSA ID or do you have a GitHub ID isn't enough. You obviously need to find out if it's the right kind of thing, which means authorization. But OAuth lets you do lets you attach scopes to tokens so that you can say things like, please allow me the power to interrogate your account for what groups it belongs to. As soon as you do that, you can build group whitelists and group blacklists to say, all right, users in groups A, B, and C should be allowed to log in unless the user is in group D, E, or F, in which case that user should not be allowed to log in. We use both of those at NCSA, and it has worked very well for us. So just in your Jupyter Hub configuration file, you simply create a subclass of the OAuth authenticator to implement whatever policy you need. Problem 3 is something that may not be obvious, but if you are going to have possibly multiple copies of your data around, or your data is sharded between different sites and you're putting the code next to the data, it sure would be nice to have consistent users at each site. Turns out that both GitHub and and NCSA, as exposed by CI Logon, provide you with 32-bit unique user IDs. That's handy. Linux also has a 32-bit UID field. So just map them together, and guess what? You've suddenly got a globally unique user ID. Likewise, the groups have have unique identifiers that map to Unix group IDs. So you can construct a user profile that works everywhere, that is consistent, and it's great. If you're using Google as your authentication provider, you're going to have your own 64 to 32-bit mapper there, because Google UIDs are a little bit longer. So, fourth problem is persistent storage, right? These are astronomers, they're working on difficult problems. They're certainly going to want to use stuff across multiple interactive sessions. Now, you could just say, well, do your work, push it to GitHub, pull it back down the next time you work. We do not think that our users would be very happy with this. So we're just doing a traditional file system, in this case NFS. Performance hasn't been great. We may be moving to GPFS as soon as there's a more robust solution for a GPFS driver within Kubernetes. But the great thing is, because we just went to the trouble of getting consistent user IDs and group IDs, all of a sudden the who gets to see what problem collapses to the 30 years solved Unix problem of file system permissions. Plus, okay, the 15-year-old problem of POSIX ACLs on top of it if you want. At any rate, because our users do tend to be fairly established astronomers, they understand POSIX file systems. This looks very familiar and homey to them. So no matter what we eventually end up doing for a backend, it's going to be presented to the users as POSIX file systems. The fifth problem is, how do you keep your users from messing with the environment and messing with each other? So how do you restrict the access? And our answer to this has been to provision the container as root, but since we have a username, a UID, and a set of GIDs, we can then provision a user with exactly those characteristics, sudo to the user before we start the JupyterLab server, and then by the time the user has any way to connect to the system, they are themselves an unprivileged user. They don't have sudo, they don't have sudo, they don't have any way to get to root, right? If you try to get to sudo through the terminal, it looks a lot like that, where you just get told, nope, you can't do that. So then the sixth problem is auditability and maintainability. How do you do this how do you provide the science stack, and how do you provide the infrastructure on an ongoing basis? Well, right, it's a container. Assuming that you're not pinning everything to latest and that you're not doing a wild update at the beginning of each build, which, to be fair, right now I am, but as we go into production, I will actually lock down the versions, then you know what's in the container. So it is completely reproducible, it's immutable, That, in turn, lets you do all sorts of cool replicability stuff with regard to, I used this release of the data with this version of the container, and anyone should be able, well, anyone with the appropriate data rights should be able to exactly replicate that environment and do their thing. We also, rather like CERN, have an options form that we use to spawn. And from this, you can see that users get to select, well, in our case, the 3 most recent dailies, the 2 most recent weeklies, or the last release version. There's also another option to let you pick whatever version if you need something historical, or if you've been building experimental versions not tagged with the magic format that marks something as daily or weekly or release. You can do that. We give you a choice of machine sizes and a way to clear your .local directory. Now, the thing about that is that we had to give users a way to install their own software. This turns into either pip install --user, or it turns into the conda moral equivalent. The problem with that, as we found out the hard way, is that users often have good ideas about what should be in the system. So they'll put something in their own environment, and then a few weeks or months later, we'll decide to build that into the stack. And then all of a sudden it comes up and their version is no longer compatible with the installed version, and their container won't start or things are broken. Putting this on the options form to let them clear the local directory is huge, because it gives them a self-service way. You know, they complain, you say, well, try that, it'll move it aside, then you can bisect and pull the things back in you want, and almost all the time that's actually enough to fix the problem. Then the last problem is startup time and user frustration. Now, you may not have this problem. In our case, the stack images are multiple gigabytes each. Now, the obvious answer in the containerization world is, they're how big? What? Stop doing that. Don't do that. That'd be nice if you can get away with it. The analysis stack is also really big and complicated and encodes thousands of years of astronomer work. And I could cut them down some, but I'm not going to get them down below a gigabyte no matter what. There's just that much code in them. So what we do is we cheat. We're already building our nightly releases with CI system. So once I've built an image, I've got a pre-puller, which is stolen more or less directly from Zero to JupyterHub, that downloads those images. And then generally, by the time people get in the morning, stuff's been built, it's been pulled to all the nodes, and startup is effectively instantaneous. My users are happy, I'm happy, and I had to do very minimal work to make that happen. So that was the lightning overview of what we ran into and how we solved it, and more or less how our system hangs together. These are all excellent resources. Zero to JupyterHub is probably the thing you should consult first for design patterns for doing your own Kubernetes and Jupyter environment. The Gitter is the sort of community development forum. Very friendly, very useful. I absolutely recommend joining it. And then our implementation is up on GitHub there. Feel free, it's all MIT licensed, to loot it for what you like. So this is just a picture of the interface we've got with some LSST stuff in the upper left, the Firefly visualizer upper right, terminal window, and then a table of astronomical objects. The QR code points to this talk. And with that, does anyone have any questions?
Could you elaborate a little bit more about GPFS and Kubernetes?
Yeah. GPFS, currently there is an experimental driver called maybe Unity, something like that, that is out there. I think at the moment it still requires the container to be marked as privileged, which is something we're trying to avoid at NCSA. And it doesn't feel like it's quite production ready yet, but we're hoping it'll get there soon. I imagine that the privilege stuff is actually a feature of, at some level, of the file system driver, in that although you don't have to state the container is privileged for an NFS mount, I'm guessing that, and I haven't looked at the code, that it probably starts privileged, does the mount, and then drops privilege. And I would think any file system driver is likely to have to do that, but don't know.
I was going to say, if I could respond to that, was that at containers we run a rancher-based
Okay.
But we have an NFS gateway to our GPFS files that we've gone with for
Okay.
that.
Yeah, which is what we're doing, that we are re-exporting GPFS as NFS at NCSA. Have you been happy with the performance you've gotten? I mean, it may be that it's just our installation that is not properly tuned.
Yeah, we were a little worried about it at first, but it's been fine.
Okay, good to know. Thank you.
One thing that we've been doing something similar to Space Telescope, one of the biggest learning curves is that, okay, we just figured out Kubernetes 1.7, hey, we gotta learn how to plug on. Are you planning on pinning to a Kubernetes version, or
A lot of that's going to turn out, a lot of that will depend on what the Kubernetes release cadence is by the time we're ready to go operational. As it is, I've been pretty aggressively chasing stuff like having binary config maps turns out to be huge for our front-end landing page, but that requires Kubernetes 110, which, you know, our primary clustered NCSA isn't yet, although we have a test one that's at 111. So eventually we probably will pin it as we will pin versions of everything else, but not for a long time yet. Yes?
really impressive work. It's just fantastic.
Thank you.
I'm just curious, like, I think a lot of scientists are interested in this paradigm of, you know, bringing the analysis to the data. There's many scientific fields. You know, some of the other options that people have are to work within the existing, you know, supercomputing infrastructure, which, you know, there's already a lot of money invested in that infrastructure, or to go to commercial cloud infrastructure. You know, you're already Kubernetes. I expect it's obvious to you, but maybe it's not obvious to everyone why you went the sort of route you went with your own on-premises, you know, data center as opposed to going one of those.
Right. So I am doing all my prototyping on GKE. Effectively, this project has been under development a long time. NCSA won the bid to be our primary data center before the big cloud providers were particularly credible alternatives. That decision was made in 2002 or something, so quite a while ago. That said, one of the nice things about prototyping this as a Kubernetes application has been that I do get to really rapidly iterate my deployments at Google, and to some degree, right, that keeps our providers honest. NCSA doesn't have much choice but to provide us a nice, useful, working Kubernetes implementation, because we can state this is the platform we're deploying it on, and hey, look, here it is running over there. I mean, that helps to motivate them to provide us with the service we will find most useful for deploying our analysis stack.
Thank Adam one more time, and I really encourage you to continue these conversations over lunch.
Just find me. I'll be here today and tomorrow. I'll be happy to give you a demonstration of our environment. Yeah, I'm around. Thank you.
Thank you.